Hi everyone, today we're going to be talking about colligative properties. Before we get into what a colligative property is and what examples of them are, I want to go over a few definitions. The first definition is dilute versus concentrated. So we use these terms when talking about solutions. And when looking at solutions, we care about the amount of particles that we see per a given volume. Dilute and concentrated are relative terms. There is not a certain solution where we say, oh, this one is dilute versus this one is concentrated. But when comparing two solutions to each other, we can apply these terms. A dilute concentration is one that has relatively low number of particles per volume. And when measuring volume, we're going to measure in a lot of different ways, often liters or milliliters in this class. A concentrated solution is one in which there are high number of particles per volume. So again, we're not really using these to say, oh, this solution is concentrated versus this one is dilute. But when we're comparing two solutions to each other, we can say this one is more concentrated or this one is more dilute. So in this diagram here, I see 4 particles per the volume, and let's just say it's a liter. And in the other beaker, I see 24 particles per volume. So we're really counting the number of particles or number of solutes in our solvent, and that can kind of give us an idea about how concentrated the solution is. Concentration itself is a measure of the quantity of solute per volume of solution. So we're looking at how much solute we have in a given volume of our solution. We can calculate this a lot of different ways. In Chem 2, we're going to look more at doing bigger calculations to find out what the true quantity is. But in this case, we can just kind of count what we see in the beakers. We've been talking about ionic and covalent molecules a lot in this class. They behave differently. They have different properties. And so they also behave differently in terms of when they're in solution. Here we're going to draw an example of what an ionic compound does when it goes into solution. And when we say that something is in solution, we often mean that it has been dissolved in a substance, and a lot of times in this case we're talking about being dissolved in water. So in this beaker here, we're going to look at NaCl, which is an ionic compound. It is between a metal, sodium, and a nonmetal, chlorine. And what does it look like when it dissolves in solution? What does it look like when it dissolves in water? Ionic compounds, when they go into solution, what happens is they break apart into their individual ions. So when I take NaCl and put it into solution, it's going to break apart into its ions. And so we need to remember how to take ions apart. We're always going to separate it into the metal side and the nonmetal side. So I'm going to separate sodium on one side, chlorine on the other. From the periodic table, I know that sodium has a +1 charge and chlorine has a -1 charge. So in solution, what we're going to see is a sodium ion and a chlorine ion separated from each other. They take on their charges. This is a solution of water, and we talked about this when talking about how molecules dissolve. But what's going to happen is the water molecules are beginning to surround the ions. The ions have charges. The water molecules are polar and have partial charges, and so there's going to be attraction there. In a water molecule, the oxygens are partially negative and the hydrogens are partially positive. So what we're going to see is a water molecule, when it surrounds sodium, the oxygens are going to be pointed towards sodium. And when it is surrounding chlorine, the hydrogens are going to be pointed towards the chlorine. And so you can just imagine that there are lots and lots of water molecules surrounding these and dissolving the ion. If we look at another compound, CaCl2, this one is also ionic. Calcium is a metal, chlorine is a nonmetal. What happens in this case is it's going to split up into a calcium ion and a chloride ion. But in this case, you notice that we have 1 calcium and 2 of these chlorines. So the total number of ions we see in this container is going to be 3. And I'm getting the 1 calcium from this imaginary subscript there and the 2 chlorines from this imaginary subscript there. So in our beaker, what we're going to draw is we're going to actually write calcium 2+, and we need to write both of the chloride ions. And then again, we'll see water surround them similarly, with the negative side of water attracted to the calciums and the positive side of water attracted to the chlorines. So ionic compounds, they split up into solution, and they specifically split up into the number of ions that we're looking for, or the number of ions that came together to form the compound. So for NaCl, there were only 2 ions, so we just drew 1 of each. But for CaCl2, there are a total of 3 ions, so we have to draw all 3. So I'm going to write ionic compounds. They split up in solution. When looking at covalent compounds, the covalent bond, in a covalent compound, there's covalent bonds. Electrons are being shared. And so those bonds do not split up when they go into solution. An example of a covalent compound is one like this. It is between all nonmetals. This is actually the compound for glucose. Covalent compounds are going to stay together as one particle when they go into solution. So I'm just going to draw my C6H12O6 staying together as one thing in solution. And then if I drew the Lewis structure, the molecular geometry of this, I could show that water is going to be attracted to the negative part or the positive part. So covalent compounds do not split. Colligative properties are properties of solutions that differ from properties of a pure solvent. So we're looking at the property of a solution that might be different than when we're looking at that compound when it's a pure solvent. So we're looking at how does sugar behave in water as opposed when sugar is just by itself. These things depend on the quantity of solute molecules or ions that are dissolved in a solution. In order to figure out the quantity, we need to both consider the concentration, so how many of the particles we have. We're going to measure concentration, maybe 10% concentrated, 20% concentrated, etc. There's also a measurement called a mole or molarity. We don't really need to worry about this unit that much until Chem 2, but you will see the notation of 1 molarity or 2 molarity. Just know the bigger the number is, the more concentrated something is. So colligative properties depend on quantity. We're going to consider the concentration, so how many particles we have, but then also the number of ions or particles that the molecule splits up into. And so this is why we need to know how many ions an ionic compound is going to split up, or know that a covalent compound is not going to split up at all. There are a handful of colligative properties. We're going to focus on just 2 of them. The first one is called freezing point depression. What this means is that the freezing point of a solution, so not a pure substance, the freezing point of a solution is lower than the freezing point of a pure solvent. The freezing point of a solution is slightly lower than the freezing point when it is a pure solvent. Solute particles, so the particles that are being dissolved in our solution, they prevent solvent molecules from coming together and packing tightly into a solid. So if I have a solution here, and let's say this is just water, when this water begins to freeze, the water molecules need to come together, form intermolecular forces, and they need to be able to get packed closely together. When there is a solute in there, like NaCl, the water molecules are still trying to come together and pack tightly in order to freeze. But what we notice is that now there are these ions getting in the way that are preventing the water from getting close together and packing tightly to form a solid. What this means is that a lower temperature is going to be required in order for the solid to form. So we're going to have to freeze at a lower temperature, get lower and lower and lower in order for the molecules to be able to get close enough, the water molecules to get close enough to freeze. So when we have solute particles, we have an ion involved. The freezing point of my pure substance, which in this case is water, the freezing point gets lower. In order to freeze, the water needs to get close together, and the solute particles are preventing the water from getting close together and freezing. So we just need to get a lower temperature in order for it to happen. So we're going to consider two different solutions. We have a 1 molar of NaCl and a 1 molar of calcium chloride. And we want to figure out which one is going to have a lower freezing point. In this case, we should know that the more particles you have, the more solute particles, the lower the freezing point. The more particles you have preventing the water from coming together, the lower the freezing point is going to be in order for the solution to freeze. In this case, these two solutions have the same concentration. So all we have to consider is the number of particles that we see. The one with more is going to have a lower freezing point. So more particles of solute equals lower freezing point. We just did this example. NaCl, when it breaks apart into solution, it breaks apart into two ions, one sodium and one chlorine. Calcium chloride, when it breaks apart into solution, it breaks into three ions, one calcium and two chlorines. Because 3 ions is greater than 2, the calcium chloride calcium chloride with water is going to require a lower freezing point in order to freeze. The other colligative property is called boiling point elevation. So we're looking at kind of the opposite end of our heating curve here. The boiling point of a solution is higher than the boiling point of a pure solvent. So when we have solute, we're going to have a higher boiling point than when we just have a pure substance. What's happening is solute molecules attract and hold solvent molecules in the liquid phase. So attracting and holding, what's happening here is intermolecular forces. The solute molecules are attracting the water molecules or whatever solvent is at play, preventing them from getting further apart. There are intermolecular forces involved that are causing attraction, and in order for solutions to boil, we have to break those intermolecular forces. With the solute, we just have more of those attractive forces, and so it requires more energy to break them all apart in order for the solution to boil. So if I'm going to draw, let's say we have NaCl in here again. We have water molecules at play, and we see that there's intermolecular forces between the water molecules and the solute. And so we need energy in order to break these intermolecular forces apart. With the solute, there's just a lot more of those connections, And so it's going to require a higher boiling point. We're going to need more energy, a higher temperature in order for the solution to boil. So a higher temperature is required for boiling to occur. Again, we have two examples here, one of 0.5 molar NaCl versus 1 molar NaCl. In this case, we're looking at two solutions with the same solute. And so in order to consider which one is going to have a higher boiling point, we need to look at the concentration. When we have a higher concentration of particles, that means that there are more particles per the volume, and more particles is going to mean a higher boiling point. So in this case, because 1 is greater than 0.5, this is going to have our higher boiling point. When you have example with the same concentration, you need to look at the actual solute and figure out how many particles do they split up into, if any. And then if you have two solutions with the same solute, you need to consider the concentration. It'll either be given in molarity, and then you can just look at the integer numbers, or it'll be given in percent, and you can consider that percentage. There are times when we combine both, we change both the concentration and the solute. So for example, here we have 3 molar NaOH versus 1 molar NH43PO4. So the solution, the concentration and the solute is different. So we have to consider how many particles it's going to split up into. Again, more particles means higher boiling point or a lower freezing point. What we do in this case is we're going to multiply the number of particles by the concentration in order to figure out how many they have. So NaOH, we know it has a 3 molar, that's its concentration. This molecule is going to end up splitting into 2 ions. We have to recognize that we're going to split this, and we're going to split my compound into metals and nonmetals. So Na goes on one side, OH goes on the other. Sodium is a +1 charge. We get that from the periodic table. And in order to cancel out that +1 charge, my OH needs to have a -1 charge. There's only one of each of them, and so it's just going to be 2 ions. 3 times 2 is 6, and so this substance will give off 6 ions. For this substance here, we have a 1 molar concentration, but this compound is actually going to split up into 4 ions. You can kind of look at the compound itself to give you a hint. There are 3 of this NH4, and the PO4 is not in parentheses, so there's only 1 of them. So we can sometimes just look at the subscripts to figure it out. So in this case, it is going to split up into 4 ions. 4 is still smaller than 6, and so this compound here will give off more particles and will have the higher boiling point. When putting this all together, we can take our understanding of colligative properties and apply it to our heating curve. This is a normal heating curve here where we have a solid, a liquid, and a gas phase, and then the transitions between them. What's happening with what's happening when we add a solute to our solution, we end up extending the liquid phase. So this is an example of a solution that is a pure solvent. We have a solid, a liquid, and a gas phase, and the transitions within them. When we add a solute, we lower the freezing point. This is the freezing point here for a pure solvent. With solute added, we lower this freezing point to maybe somewhere like here. And so this part of the liquid phase has been extended. Our boiling point of this pure solvent is here. With a solute, we are increasing the boiling point to maybe here. And so this part of the liquid phase is increased. So with solute added, we are elevating the boiling point and depressing the freezing point, making the liquid phase of the solution longer. There are more temperatures at which the solution is a liquid. So we call this an expanded liquid phase.